Lambrechts, who is a researcher at IMEC. And IMEC is a research facility in Leuven, Belgium. And they work closely with a number of partner institutions on a variety of different research projects. And he's going to tell us about some of the work they're doing with multi and hyperspectral imaging and holography. So tell us about these technologies, and then you have some demos for us.
Yeah, hi. So today we're presenting here some very interesting technology results we have achieved in hyperspectral imaging, as you mentioned, right, and in holographic displays. So we can move over here and I can show you something about hyperspectral imaging and why we want to use it. So at IMEC we have developed hyperspectral imaging modules, which is a combination of the sensor and the hyperspectral imaging filters. We're trying to really bring hyperspectral imaging to the industry, and this is a demo which we can show here, which really shows the potential. So on the left here, there is a scene which we composed of various green objects, in this case leaves. So what the problem is in various industrial applications where you, for instance, want to do food sorting, is that the current cameras cannot see all the information we're looking for. So in this case, we here have a scene where the little round regions indicate to the software that we want to make a difference between different types of leaves. In this middle image we have a hyperspectral image of the same scene, and in the right image we show what is actually the content of these objects which we've put here. For instance, the red ones are real leaves, the green ones are fake leaves which we printed on paper. The top one and the bottom one here, they're the fake leaves which we bought on the market, so they look like leaves, but in reality they're actually a combination of plastic and fabric. And the purple one here, that's also a plastic leaf. So in the normal view they all look the same. So what we can show now is that if we do a software interpretation of this scene, then now in real time we will compute what the software thinks we see in the scene based on the round regions which we've indicated. So in this case, based on a normal color view, which is taken by a standard RGB camera, the software makes a number of errors. So the scene doesn't have enough information, or the camera cannot see enough information to do this correctly. So in this case, we see there are a lot of differences between the software results and the scene as we put it together. Now, if we do the same thing for the hyperspectral image, and we load the same training set, so the same round regions which indicate to the software what we're looking for, and we ask the software to analyze this scene, starting from the hyperspectral image, the software will have much more information to work with, because the hyperspectral camera can do a much more detailed view of the scene. In this case, the software is perfectly capable at a pixel level to find back what class all these objects belong to. So now we can maybe move over to what we are doing at the technology side. So basically,
Let me get next to.
if we look at current hyperspectral systems, we have seen that they're very bulky, very costly, and very slow. And especially slow is a big problem if we want to use this in sorting, where we want to sort, like for instance, a couple of tons of peanuts per hour. So we are not happy with systems that can only do one object every 5 minutes. So we really invested in making this technology really fast and really industry ready. So in this case, what we are doing is we are post-processing a range of hyperspectral filters that can really be tuned to the application. We post-process them directly on top of image sensors. And by doing that, we arrive at a very compact and very powerful hyperspectral module, which is orders of magnitude faster than what is currently available in scientific instruments for hyperspectral imaging. So these wafers show some demo models which we have of those hyperspectral filters, and we can really tune those to customer needs. We can also select the image sensor to post-process on top of, based on what the customer and the application really requires. Okay, so today we also have a demonstrator here for our holographic TV. So this technology, in this case, the demonstrator is a static mask which contains a 3D data set. So the goal of this project is we will build a dynamic version of this, where with MEMS technology we can do moving images of this same technology. But let me show to you what the point is. So in this case, you can't really see anything with the naked eye because it encodes a 3D scene. If I illuminate this scene with the laser, on the white background you will see a cut through this scene. So certain objects in this scene will be in focus and others will be not. So in this case, you will see multiple cubes, and as I move them, some of the cubes will come into focus and others will be getting more blurred. So all the cubes are encoded at different distances. So for instance, in this case, you will see the B cube is pixelated, which means it's not in perfect focus. And if I move back, or to the front actually, in this case the B cube is in focus, so you don't see the pixels anymore. So this will allow us to encode a 3D scene, and then with a moving chip we can have 3D television without glasses. And if we illuminate this chip with 3 different colors, it will be possible to do color images with this.
I'm here with Bob Murphy at Opnext, and Opnext is a laser diode manufacturer, and we're going to talk about some of the products that incorporate laser diodes. The uses now, as people know, are tremendous in consumer electronics and in biomedical. So Bob, why don't you tell us about some of the things we're going to see here?
Great. Well, thanks very much. At Opnext, we address many different markets with our laser products, and a couple of them we'll talk about are the light blue optics projection, as well as our AccuVein vein detection system. Now, the light blue optics is really cool in that they can, at a virtual projection system, this could be set up as a keyboard, it could be set up as a menu in an operating say at a restaurant. You can show videos, for example. And let's have a look at Casino Royale trailer. And it takes a moment for it to load up. And then it will play. And then it will play. There we go.
There we go. I can always edit that out.
Alrighty. So here is the Casino Royale trailer. And of course, it's very bright light in here, but there's still good visibility into the video. Of course, these are black and white scenes. But when we go into the full color scenes and the motion, here it comes in. It's really quite nice. We actually have a customer that has set this up in a restaurant, so you can order a martini. You can order a beer, you can order the food, and then someone will bring it. You can almost imagine that eventually it'll be a robotic delivery. It's really amazing. The other product, this is a company called AccuVein, and they're using our red laser to illuminate the veins in your arm. So in a hospital or a doctor environment, when you go to give blood or they have to give you a shot, sometimes the phlebotomist has to, fish around a little bit for the vein, and that can be a little painful. So, Tom, let's maybe we'll use your other arm. I don't know if you can get that. You can see his vein there.
Wow.
So if I was a person that had to give a shot, I could zoom right in on there. If that vein collapsed, maybe I could go over to that one. And you always wonder why they always do this to you before they give you the shot. Well, look how much that expanded. I always thought that maybe they were telling me to sit still or something. So it's the applications for our devices it just boggles the mind. And every time I visit a new customer with a new application, I'm surprised and amazed at they can take our laser and create systems for unbelievable amounts of products. It's fun.